If I were to describe the relationship between the number of red Lego pieces and the number of blue Lego pieces, I could say quite simply there's one red Lego piece and two blue Lego pieces. I could fancy that up a little bit and I could say something slightly more technical sounding just to seem fancy. For every one red Lego piece, there are two blue Lego pieces. There is one red Lego piece, and for each of those one red Lego pieces, there are two blues linked to it. These kind of relationships are quite helpful. This kind of, for every one of something, there are a certain number of something else. So being able to write that much quicker than having to write that full sentence will be a particularly helpful thing. So what we do is we use a particular piece of notation. I'm going to write, first of all, the number of red Lego pieces there are. There is one red Lego piece. And I'm going to write also how many blue Lego pieces there are. There are two blue Lego pieces. And I'm going to use a symbol in the middle. And that symbol in the middle is going to stand for the words, for every one of these, there are two of these. For every whatever is here, there are however many of these there are here. And the symbol I'm going to use is two dots like this. This, in maths, is called the ratio symbol. And it means for every. So there is one red for every two blue. Now what I've done is I've repeated that pattern. So I've put another one red and two blue down. The link between red and blue is that for every one red we have two blue. So I've put that down again. Now what we have is not one for every two. Surely we have two red and we have four blue. And we have a ratio of 2 to 4. For every two red, there are four blue. We absolutely do, because this describes how many actual pieces there are there. There are two red and there are four blue, with this ratio link in between them. But if I were to put a box around those and a box around those, we would see surely that for every one red we have two blue. For every one red we have two blue. So this first one here is also true. Turns out that what these ratios are, they are said to be equivalent. Meaning the same thing, giving the same information, but written in different forms. So this second one describes how many pieces are actually there. The first one doesn't, but it gives the same relationship. We can continue this idea. I've repeated the pattern again. We now have 1, 2, 3 red, and we have 2, 4, 6 blue. So we have a ratio of 3 to 6. Where we read the ratio as the first number to the second number. That ratio symbol means for every and gives that link, but it's often read as 2. 1 to 2, 2 to 4, 3 to 6. But again, we have this same link where I can put a box around those, and we still have, for every one red, we have two blue. 2 blue for this red, 2 blue for this one red, and 2 blue for this one red. So this first one is still true, which means that this first one and this last one are also equivalent. Different ways of describing the same relationship, where this 3 to 6 is the one that describes how many pieces are actually there, and this first one just describes the relationship in a much simpler way. So if we just look at these pairs of equivalent ratios a little bit more closely, first pair we've got is 1 to 2 and 2 to 4, and we showed through those Lego pieces that those two ratios are equivalent. Now what's actually happened between the first form of that ratio and the second form? Well, if we look at the red numbers, what's happened to the red numbers is we've gone from 1 to 2, we've doubled it, we've times it by 2. And notice that the same has happened on the right hand side of the ratio, the blue side. We have timesed both sides of the ratio, left and right, by 2. Notice that it would also work the other way around. If we'd started from this second one and gone down to the first one, we'd have divided both sides by 2. We'd have gone 4 divided by 2 is 2 and 2 divided by 2 is 1. And we'd have still found an equivalent ratio. With the second one, the 1 to 2 and the 3 to 6, notice that we have times both sides of that ratio by 3. And in scaling both sides of the ratio up by the same amount, we have found an equivalent ratio. And again, the same link works if we go the other way. If we start with the 3 to 6, divide both sides by 3, we would get down to the 1 to 2. And we found an equivalent ratio. So to find an equivalent ratio, we just need to scale both sides up or down by either timesing or dividing by the same number. Fill in the missing numbers to make the ratios equivalent. So we'll have a look at this first example, 1 to 2 and 10 to something. To make something equivalent, to make two ratios equivalent, we have to scale both sides up or down by timesing or dividing by the same number. So we've gone from 1 to 10. And going from 1 to 10, we have timesed the left-hand side by 10. To make it equivalent, we also have to times the right-hand side of the ratio by 10. Otherwise, we are just coming up with a different relationship. Remember, a ratio just describes a relationship, so we're making it 10 times bigger on the left and 10 times bigger on the right. And we're coming out with 20 for our equivalent ratio. Second one, 3 to 5 and something to 25. Well, again, we look for what we've timesed or divided by. And to go from 5 to 25, we have times by 5. If we've times by 5 on the right, to keep things equivalent, we have to also times by 5 on the left. And we're going to do 3 times 5, and that's going to give us 15 to 25 for our larger ratio. And finally, the last one, 4 to something and 20 to 5. Looks a bit weirder because the bigger number is first, but actually we put them in the order that the relationship is read, and it so happens that whichever one we came to first had 20, and whichever one we came to second had fewer at 5. We're going to go from the complete one down to the incomplete one. So we're going from 20 down to 4, which means we have divided by 5. And if we've divided by 5 on the left, we should also divide by 5 on the right to keep the ratio equivalent, which means we're going to go 5 divided by 5 is simply 1. And our equivalent ratio is 4 to 1. Consider the ratio 280 to 320. Perfectly reasonable ratio. It means we have 280 of one thing and 320 of another in that relationship. Problem is, these are quite big numbers, and they're quite difficult to conceptualize. They're quite difficult to put in our minds and think about 280 of something and 320 of something. They're too big to really mean very much to us. So maybe we could use this equivalent ratio idea to make these numbers simpler. And rather than timesing the numbers up to find equivalent ratios, why don't we divide the numbers down to find equivalent ratios? Because if we do that, we can make the numbers smaller. So we could look at the 280 and the 320 and we could ask ourselves, look, is there anything that we could divide both sides by? Is there anything that both sides will divide by? And if there is, then we could do that and make the numbers smaller. And in making them smaller, they might be easier to work with. We might, for example, notice that both of these numbers end in a 0. And in ending in a 0, that means that both numbers will divide by 10. They are both multiples of 10, so they must divide by 10. Let's do that then. Let's divide both sides of this ratio, left and right, by 10. Because we can make the number smaller, and we can do this because we're just writing equivalent ratios. Maybe the equivalent ratio isn't going to describe what's actually there anymore, but it is still going to describe the same relationship. 280 divided by 10, it'll shift things down the columns in the 100 units grid and give us 28. And on the right hand side, 32. And already we're dealing with a much simpler ratio, 28 to 32. And we can picture that a bit more easily. But why don't we see if we can do this again and make these numbers any smaller? And is there anything else that they will divide by? Well, they're both even numbers, so they will at the very least both divide by 2. And dividing by 2 is not that difficult a thing to do, so let's do that. Let's divide them by 2. Let's do 28 divided by 2 to get 14. And let's do 32 divided by 2 to get 16. And end up with the ratio 14 to 16, where again this is an equivalent ratio. Different number of things there, but meaning the same thing, giving us the same relationship. Is there anything that they will divide by? Well, they're both still even numbers, so we could divide by 2 again. We could divide by 2 on the left and on the right. And we do 14 divided by 2 is 7, and 16 divided by 2 is 8, and we will be left with the ratio 7 to 8, which again is much simpler and much easier to work with, much easier to picture. Is there anything that they will divide by? Well, actually 7 is a prime number. The only things 7 will divide by are 1 and 7, and 8 will divide by, well, it won't divide by 7. It would divide by 1, but we wouldn't be changing anything. So it turns out that that is as far as we can go. But we could do this for any kind of ratio. We could start with quite big numbers, or even not so big numbers, and we could kind of cancel things down, break them down, dividing left and right by the same thing until we can't do it anymore. And this, 7 to 8, is called the simplest form. 7 to 8 is the simplest form of 280 to 320. Well, we've broken that down into equivalent ratios until we can't do it anymore. Not without putting decimals in anyway, and ratios we want to try and stick to whole numbers where possible. There's nothing wrong with having a decimal in a ratio, it's just that certainly the simplest form we want to keep with whole numbers, because if we're looking for a simplest form, a nice easy way of writing something, decimals doesn't tend to lend itself very well to that. So this is as far as we can go, and this is the simplest form. So actually, what this question could have said was, write the following ratio in the simplest form, or find the simplest form of the ratio 280 to 320, and you would go through this process and get down to 7 to 8 being the simplest form. So, write these ratios in the simplest form. 5 to 15, first of all, we look for something that both left and right will divide by. And clearly both left and right will divide by 5. They are both in the 5 times table, so we can divide by 5 on the left, and we can divide by 5 on the right. 5 divided by 5 is 1, and 15 divided by 5 is 3. That is as far as we can go. We should always ask ourselves, is there anything else that they will divide by? But actually in this case there isn't, and 1 to 3 is the simplest form. 12 to 18 over here, we look for anything that both numbers will divide by. Now, sometimes you might see that there is a fairly big number that things will divide by, and you might be able to do this in one step. Sometimes it might take you more than one step. It depends how good you are with your multiples, your times tables, that kind of thing. If in doubt though, there are a couple of easy checks that you can look for. You could look to see whether it divides by 10, because that's a reasonably easy thing to do. Or you could look to see whether something will divide by 2, because that's also a reasonably easy thing to do. This will divide by 2, because they are both even numbers, so we could do that if we wanted. We could do 12 divided by 2 and 18 divided by 2 to get 6 to 9. And then we should always ask ourselves, is that the simplest form, or is there anything else that they will both divide by? And it turns out that they will both divide by 3. And because we're looking for the simplest form, we should do that. So we should break these down again. 6 divided by 3 is 2, 9 divided by 3 is 3, and we get 2 to 3. And then we ask ourselves, is that the simplest form, or is there anything else that they will both divide by? Well, 2 will divide by 1 and 2, 3 will divide by 1 and 3, so the only thing they'll both divide by is 1, and it won't change anything. That must be the simplest form. Notice though, if you looked at 12 and 18 and said, they'll both divide by 6, you would do 12 divided by 6 to get 2, 18 divided by 6 to get 3. You'd have got to exactly the same answer, just slightly quicker. So either is fine. You can do it in one step, you can do it in more than one step. There is only ever going to be one simplest form for any given ratio, and you will reach it as long as you're doing something valid. A plank of wood is cut into 2 pieces. The long piece is 350 centimetres in length. The short piece is 25 centimetres in length. Write the ratio of the length of the long piece to the length of the short piece. Give your answer in the simplest form. So it's a simplest form question. We take a ratio, we cancel it down in that way we've just done, and find the simplest form. Problem is we haven't got a ratio yet. The question first of all wants us to write the ratio. Well, to write a ratio from words, all we need to do is follow exactly what it says in the words. The words tell us exactly what we need to do. Write the ratio of, there's our instruction to write a ratio. So we're going to be using these ratio dots because it tells us to write the ratio of. We just need to work out what goes on the left and what goes on the right. And to do that, we find the single most important word in this question. And the single most important word in this question is the word 2. Because 2 is the ratio dots. And whatever comes just before the word 2 goes on this side, and whatever comes just after the word 2 goes on this side. So find that word 2, write the ratio of the length of the long piece to the length of the short piece. So on this side, the length of the long piece to the length of the short piece. Long to short. Once we've found that, we then comb the question for those two pieces of information. It might be that both of them are given to us in the question. It might be that we have to do a little bit of working out to find them. Depends on the question. Sometimes they'll be given to us, sometimes we might have to find one or both of them from some working out. This is quite a generous question. They are both given to us. So the long length is 350, and there is the left-hand side of our ratio, and the short length is 25, and there is the right-hand side of our ratio. So our ratio is 350 to 25. That is the ratio we need to work with then. We need to cancel that ratio down into the simplest form. Why? Because the question says give your answer in the simplest form. This would have got us a mark. So if we did nothing else, we've got a mark on the question. But since it's not that difficult to cancel something down into the simplest form, we might as well do it. So what we need to do is look for something that both of those will divide by. This is not quite as easy to do, because our usual standbys of check 10, check 2, well, they are odd numbers and they won't both divide by 10. This will, admittedly, but this one won't. So then we think, right, what are other simplish things that we could divide by? 5. 5 is not too difficult a thing to divide by, and it will work here. If we do 25 divided by 5, we would get 5. And that was easy enough to do. Slightly harder to do, 350 divided by 5. Well, what about 35 divided by 5? 35 divided by 5 will be 7. There are 7 5s in 35, so there must be 70 5s in 350, 10 times as big, so the answer will also be 10 times as big. And we get simply 70 to 5. And then we ask ourselves, is there anything else that it will divide by? Well, much as these ended in a 0 and a 5, these also end in a 0 and a 5, and anything that ends in a 5 or a 0 will divide by 5. So it turns out that we could divide by 5 again. We could do 5 divided by 5 on the right-hand side to get simply 1. And we could do 70 divided by 5 to get, well, 70 shared between 10 will be 7. Sharing it between 5, if there are half as many people, it'll be twice as big, so 70, or you could just count up in 5s. Either way, we get 14. 14 to 1. Is there anything else that they will both divide by? Well, no, because the only thing that 1 will divide by is 1, and that's not going to change anything. So our simplest form, 14 to 1. Simplest form, remember, doesn't necessarily mean simple form. Write the ratio 2 to 3 in the form 1 to n. And a perfectly reasonable question to ask would be, what on earth does that mean? Okay, step back. Ignore the 1 to n for the minute. 2 to 3 is a ratio. Perfectly reasonable ratio. For 2 of one thing, we have 3 of something else. 2 to 3 is also a ratio in the simplest form. There is nothing more that we can do to that to cancel it down, assuming then that the simplest form has to contain those whole numbers that we like and not decimals. Well, let's think about this 1 to n then, and what on earth this might mean. 1 to n. Well, really, that n is just a placeholder. We're using the letter n, where we could perfectly reasonably instead use a question mark. So we want to write this ratio as 1 to something. Why an n? Because it just is. N for number, if you like. We're using an n as a placeholder where we could otherwise use a question mark. So really what this question is saying is write the ratio 2 to 3 in the form 1 to question mark. As in, this is the simplest form, and there is nothing else we can do to that, unless we are asked to do exactly this to it. We are going to cancel it down further, past the simplest form. And we're going to do it to force that first number to be 1. Why? Because we are told to write it in the form of 1 to something else. So cancel the ratio down further, past the simplest form, to make that first number 1. How do we do that? Well, we would divide the left-hand side by 2. 2 divided by 2 would give us 1. Now, to keep this equivalent, because even in this weird form, we have to be sticking with equivalent ratios, this 1 to n means make the first number 1, and the second number then will be whatever it needs to be to keep the ratios equivalent. 1 to n, 1 to question mark, 1 to whatever the number comes out as. i.e., in this case, divide the second number in the ratio by 2 as well. Now, yes, this is going to give us a decimal. The only reason we're going to allow the decimal in this example is because we are specifically told to cancel the ratio down further past the simplest form to make sure that the first number in that ratio is 1. We'll do 3 divided by 2 and we will get 1.5. Again, there's nothing wrong with having ratios with decimals in them, it's just that we don't like them, so we try and avoid them where possible. But we have been specifically told to cancel this down into the form 1 to n, 1 to something, or more precisely, 1 to whatever needs to be in that second place, so that the first place can be 1 and we can keep an equivalent ratio. In this case, the n is a placeholder for 1.5. Write the ratio 10 to 4 in the form n to 1. Same kind of thing this time. It's just that this time the 1 is in a different place. What we're saying is, yes, we could cancel that down to the simplest form. If we cancel it down to the simplest form, incidentally, we'd get 5 to 2. But we're not being asked for that. We're not being asked to write the simplest form. We are being asked to cancel this ratio down further, past the simplest form, to make the second number 1. Why the second number this time? Because we're asked to do it in the form n to 1. n to 1, or rather something to 1, because the n is just a placeholder, a letter being used to fill the gap, because it looks a bit more fancy than just using a question mark. So what we're doing is we're saying here that the second number needs to be 1, and the first number has to be whatever it needs to be to give an equivalent ratio. So for this second number, we're going 4, we're going down to 1, so we're going to have to be dividing by 4 to give us that 1 in the second place. To keep these things equivalent, we have to divide by 4 in the first place. We're going to get 10 divided by 4. Well, 10 divided by 2 will be 5, divide it by 2 again, 2.5. Where n, in this case, is a placeholder for the 2.5 that we've now found. The second number is 1 as required, n to 1 make the second number 1. And we've still got an equivalent ratio. But we've allowed the decimal this time because we're specifically being asked to make sure that that second number in this case ends up as 1. To 2.5 to 1. Final kind of ratio question you might get is one to do with sharing. Something like this, for example. Share £35 in the ratio 2 to 5. Now what this means is we have got £35, currently being represented by 35 red Lego bricks. We are going to share this out among 2 people. Why 2 people? Because there are 2 parts to the ratio. Each time we do some sharing, one of the people is going to get £2 and the other person is going to get £5. And then 2, and then 5, and 2 and 5, and 2 and 5, and 2 and 5. And we're going to keep going until there is no money left. And that's our kind of approach. So what we're going to do is we're going to take out 2 for the first person, and 1, 2, 3, 4, 5 for our second person. We could take out 2, and then 1, 2, 3, 4, 5 for our second person. We could take out 2, and then 1, 2, 3, 4, 5 for our third person. And we could keep going until we haven't got any left. And our first step is, each time we are taking out 2 and 5 is 7. Each time £7 are coming out, 2 for the first person, 5 for the second person, 2 for the first person, 5 for the second person, and so on. Now we can do that until there isn't any left. So we can take out a 2 and a 5, a 2 and a 5, a 2 and a 5, and how many times can we do that? Well, 7, 14, 21, 28, 35. That's 5 times we can do that. 35 divided by 7 is 5 times we can do that. So 5 times. So we've done 3 already. That's 4, 2, and 1, 2, 3, 4, 5. That's 5 times. Now that means if we're doing that kind of take out 7 and split it 2 and 5, take out 7, split it 2 and 5, if we're doing that 5 times, then person A gets 5 lots of the £2, and they get £10 in total. And person B gets 5 lots of £5, and they get £25 in total. If we just do a quick count up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there would be the other 25 in there. 10 and 25 do indeed make 35, and we've shared 35 in the ratio 2 to 5. Now we can actually do any of these share in a given ratio questions in exactly the same way by telling us that little story. It doesn't matter whether it's £35 or 35 things or whatever. It could be money, it could be number of objects, it could be a length that we're splitting, it doesn't really matter, but we can still tell ourselves the same story and work through exactly the same number of steps. Share £77 in the ratio 2 to 4 to 5. Now there's something weird about this ratio. This ratio's got 3 parts to it. We've never seen a ratio with 3 parts before. But actually, all it means is there are 3 people getting a share of the money. First person's getting 2, second person's getting 4, third person is getting 5 parts of it. And we can still go through this story in the same way. So we've got our £77 and we're taking some money out, and each time we take some money out, first person gets 2 of the pounds from that chunk that we've grabbed, second person gets £4, third person gets £5. So each time we take some money out, we are taking out 2 and 4 and 5 is £11 are coming out. 2 for the first person, 4 for the second, 5 for the third. Now there's a finite number of times we can do that. How many times can we take out £11? Well, we've got £77. How many 11s are there? There are 7. So 11 can come out 7 times, because there are 7 lots of 11 in the 77. And if we can do that 7 times, then that means person A is getting 7 lots of £2. So they're getting £14. And person B is getting 7 times £4. £4 each time, we're doing it 7 times, so they're going to get 7 lots of £4 is £28. And person C, this is the third person, is going to get 7 lots of the £5 is £35. So we've got 14 and 28 and 35. We could probably just check quickly that they add up to 77. If they do, the chances of these questions going wrong, but then adding up to give you numbers that work at the end, quite slim. So if these 3 numbers add up to 77, we're probably okay. We might go off to the side somewhere. 14 plus 28 plus 35, well, 30, 40, 50, 60, 68... 68 plus 5 is 73, plus the 4, 77, that seems to be okay. 14, 28 and 35. The end of these questions, it's always worth a quick check exactly what the question is asking you to do. The question might be asking you to find the 2 or 3 shares, or the question might be asking you to just find one person's share, person A, person B, or person C. It will be obvious from the answer line which one you need to give, but actually the method is the same for both types of question. Work out all of the shares because it's a good way of checking that it works, and then give either all 3 or just one of them depending on what you're being asked for.